Today's whole session is mostly about what you might call the future of computing that's different than we have today, different than these boxes we're having on our tables. And so one of the first questions that I want to pose for everyone has to do with the context that I've set up for this whole thing, and so it gives me a chance to sort of probe folks, which is how different is computing today from what goes on in nervous systems, and are we approaching that so that we want to move towards that? We want our devices to be more thermodynamic, perhaps, and so on. Or do we want our devices to be quite different than us? So that's really the crucial question that I want to start with. First of all, how different are computing devices today and brains? And second of all, do we want to move towards devices that work more like brains? And so what I'd like to do is just simply ask this question, but I'm going to introduce folks that have not been introduced yet first. And over on the far side, I have Paul Verschoor. He will be talking a few days later, hopefully sum up all of this and tell us how we've been wrong all along the way. Melanie Mitchell a little later today, a computer scientist who's been everywhere, has worked in Boston for a while and now is in Portland. Bruno, who will also be talking just after lunch, also about some of the questions that we're talking about now, and so I don't mean to steal your fire. You've heard Stéphane talking about the neural network zoo, and of course you've heard Francis Eiligan last night, who will also come back to talk about more global computational issues. So what I want to do is to begin with that first part of that question, and that is how different are the devices we use today? The way we think about computing, how different is that from the way brains work, and how similar it is? And so I don't know who wants to start with an answer to that question. Somebody has to crawl up to the microphone, yes. Or we can take the microphone out and pass it along.
Well, I can start.
You get to start, yes.
Okay, so computing devices we have today are very different from the way brains work, even though we don't know how the brain works. So this is a bit of a conundrum that we have to look at more carefully. And the second observation I would like to make, that this whole notion of Turing computation, Turing machines, it's also like a cognitive deficit, right? It's a way in which we like to think about how certain processes play out, and it has been very effective also to build these kinds of machines, but we should be careful not to apply it too broadly, right? I see it very much, so the thing, even though many people would speak about, let's say, alternative forms of computation, and they have aspirations in that direction, in the end they always get sucked into this big attractor of the Turing machine, right? So to look at the field of neuromorphic computing, which has been around now for 30 years or something like this, that always has positioned itself as offering alternative paradigms of computation, more inspired by the brain. But if you look at what they really do today, right, it can still be captured within this Turing framework, right? So this is, I think, so one issue is if we talk about being non-Turing or super Turing, what are we actually really having in mind, right? So I think we should be clearer about this. And then I'm also sure that Turing, if he would still be alive, would be suffering a lot about the way in which we have abused his thinking in this domain as well. It's not that he was that restricted. And so the second issue then is, what are we talking about when we talk about brain, right? We talk about neural networks, we saw a whole collection of neural zoo, or a zoo of neural models. There's very little neural about them. We speak about brains in metaphorical terms, right? So because something, as John Searle would say, walks like a duck and quacks like a duck, it doesn't make it a duck. So that's what we also should be clear about what we really mean when something is brain-like or brain-inspired. Right? So inspiration as a scientific method is actually not very helpful. Many things can inspire us. So there also I think we should be much clearer what we really mean when we talk about brain, and also be clear what we mean when we talk about Turing machine.
Sure, maybe a few to follow up on some of those points. I think in some sense we shouldn't even be using the word computation. to describe what brains do. It's not, well, not that we shouldn't, but it's not clear to me that's really the right word, in that, computation to most people means Turing computation, and we don't really have many other sort of examples of that. And so that sort of leads people down the road to think, oh, that's what you mean the brain is doing. And I'll just, so quote the late Walter Freeman, who used to be here. He was here at UC Berkeley for many years. And he had a very different way of looking at brain function. And in one of his talks, he referred to the so-called information processing view of neural function. And when I first heard him say that, I was shocked. I was like, how dare you think of, like, what do you mean? How could you think of it otherwise? And I came to learn sort of he had a very different way of viewing things. He thinks of the brain as a dynamical system. And to him, these oscillations that were occurring in the brain are very important. The principle of mass action. Not convinced I entirely understand everything about what it means myself, but I guess it opened my own eyes to the idea that there's a very different way of viewing the system besides the sort of standard neural network computational view that I grew up with. And I think we have to be open to that there's sort of new types of mathematics we need to think about what's in the system. We have, the computational metaphor right now is, people in the 18th century, when they were looking at the brain, they thought of it in terms of pumps and things like that. And so there's always kind of the analogy of the day that you use. And so I think we should be on the lookout for better metaphors for what the brain is doing.
So I'm not a neuroscientist, I'm a computer scientist, and I don't know that much about the brain. But let me just say one comment about how today's computers are different from people and the way they think, that I think is interesting. So we know that people are smarter than computers, of course, but there's this view in AI that eventually we'll get computers that are smarter than people, and there's this term superintelligence, right? And there's this kind of assumption that AI systems can have it all. They can have sort of the computational ability of computers, like they can multiply 50-digit numbers extremely quickly. They can be completely rational and logical and do deductions and et cetera. And they can have human intelligence without all the cognitive biases that we have, without the need for sleep, without getting bored, without emotions, and so on. And that's kind of going to be the strength of the supercomputer. We hear that superintelligent machines are going to be able to read all of human literature in a matter of mere days, and therefore have all of the knowledge, et cetera, et cetera. And I find that a little bit questionable, I guess. I'm not sure that it's clear that you can have it both ways, that you can have intelligence at human level intelligence without having all of those biases that humans have. And I can't prove that that's true, but it's just an assumption that's being made in the AI world that I think is worth discussing.
So there's two thought experiments that come to mind, which I think are related, which have always come to mind with me whenever I talk to someone who says that the mind is like a computer. So the first thought experiment is that of Burden's ass. It's I think it stems from a political discussion somewhere in the 19th century. The idea is that you have an ass, you have a donkey, which is approaching two bales of hay. And they're exactly at the same distance, they're exactly the same. And the donkey is hungry, so he wants to go to one of them, but he can't choose which one. And so in this thought experiment, the donkey gets stuck, and eventually he dies of hunger, which is, of course, a sort of absurd argument to make, because that would never happen in nature. The second thought experiment is that where the computer originally stems from, which is one of the problems posed by David Hilbert in the 1900 is the centennial problems. So two of them, the incompleteness and the inconsistency, those were approached by Gödel. And then another one, the halting problem, basically, was approached by Turing, and his solution, or his answer to this incomputability problem was the universal Turing machine. Was the idea that if you have a set of axioms and you apply them to each other, that eventually you might run into a halting problem, you might run into a loop in your computation, and this will get the computer stuck forever. And I think that reminds me a lot of this burdens as argument. It's exactly what nature not is. It's exactly not how it would work with us. So in essence, I think what Turing showed is that what a computer is not how we work. We have a metabolism, we have goals, we have a sort of overarching thought process that once we get stuck, we go do something else. And that's, yeah, to me, that points to a major difference between how our mind works and computation.
For me, one of the basic differences between computation and how the mind works is that computation assumes that you have a given input and then you need to transform it into a given output, but nothing specifies what's the input and what's the output. It's just a program that does what it gets. Well, what a mind does is a mind or a brain, it's making sense of its environment, and making sense of the environment means not just taking in what's there at the moment, processing the information, that's part of it, but it's interacting with that environment. That's what's the view of so-called enactive cognition, which is that brain and environment are in constant interaction. It's a loop that is so continuous that you can't really say where it begins and where it ends. And the point of this loop is for the organism to adapt to its environment or to adapt the environment to its own goals. It's constantly in a kind of a dance with its environment to try to get the maximum benefit out of it. And that benefit, that means what is valuable for the organism. So value is something very important, and value in particular is something that's very difficult to program in the computer. You put a utility function in there, but that utility function can only say something in a finite universe where there is a finite number of things from which you can then calculate this is that useful. But value systems in our brain are the results of billions of years of evolution, decades of personal experiences, centuries of social, cultural development, and all of them have created a very complex value system that constantly makes us see, well, this bit of hay is maybe more attractive than this bit of hay. So it's the kind of problems that he was speaking about. It's not that you need to make a choice on the basis of some kind of a logical universe where you have to compute for each of the alternative what is the utility. It's a much more encompassing, fluid, constantly adapting contextual sense of value. And that's very difficult to reproduce in a computer.
So that leads me to my next question. And my next question does have to do with value. I like to think of life as normative chemistry. Chemistry where you can get it right or wrong. Real chemistry, of course, just happens. Real physics just happens. But for living things, chemistry can be right or wrong. And so that organisms and those that end having minds at some point in evolution have all been, of course, evolved around getting it right. And one of the challenges, of course, we face when we program a utility function in, or we label the output of a neural net and say these are the ones we want, not those. We, in a sense, reinforce certain connections and so on. They're all about normative assessments, something that's right, something that's wrong. We human beings, and of course most organisms with brains, make those assessments partly on what you might call most generically feelings. That is, it feels good, it feels bad, it tastes good, it tastes bad, and so on and so forth. The question then is, do we know how to make our devices feel in that sense? And in a sense, this is what I'm talking about. It's like unprogrammed learning, but it's unprogrammed learning that uses somehow the intrinsic features of the device. That's our intrinsic features are what decide what's normative, what's good for me, what's bad for me. Can we do that with these devices?
Well, actually, it's a topic I was just a few days ago. I wrote an email to my research group because I had a new idea of what I called distributed value. The problem with value is that there is no such overarching value like this utility function that says absolutely this is good, this is bad. Everything depends on the context. The context is a complex interaction of different things. So I tried to formulate for myself what would be then value in this distributed sense where you have lots of different things interacting. And I came to the idea of what I called open coherence. And by coherence, I mean that when different things interact, you try to minimize friction, you try to minimize dissipation, you try to minimize conflict, you try to maximize synergy, you try to maximize mutual adaptation. That means you make things more coherent. But on the other hand, coherence alone is not enough because you could end up in a kind of a frozen system like, let's say, a crystal. All the atoms are perfectly aligned. It's a perfectly coherent system, but it's a frozen system. Nothing happens there. That's why I thought that next to the coherence as a value criterion, you need to have this openness to new things. So what we see in biological systems, they're on the one hand coherent. That means all the different chemical and physical processes within the organisms, they work efficiently with each other, they cooperate, they are synergetic, but they are not so synergetic or not so coherent that they are frozen like a crystal. They are open to new input, to variation, to noise, and that's what makes them evolve and keep alive.
So in machine learning, we have this term called an objective function, which is a fitness function sometimes. I prefer the term objective function because it's so confusing. Because it's not about objectivity, it's about the goal of the system where it tries to learn towards. And this is where we add the utility and where we add the value. So in supervised learning, the objective function would be to minimize the error with the labeled data set. I do see an approach also more recently towards a sort of it's not a self-generated objective function, but an objective function that is closer to the workings of the network. So, for instance, in unsupervised learning, what we try to do is we try to predict the next input value, for example. So then suddenly the outside world becomes what we try to minimize our prediction error for. Now, obviously, there's one easy way to predict exactly what your next input will be, and that's to close your eyes. So that's not always something that works. So there has to be something else as well, which is more pragmatic, which is more about what you do in the world. But it's these kind of efforts that I do see happening right now in the machine learning world. But so far, it all seems insufficient. I think it's like we have the computer, we really want it to work as a brain, but there's some fundamental steps that seem impossible to take there. So I don't think we're anywhere close to an answer there. Yeah. Sure.
I just wanted to add that indeed the criterion of being able to predict, which is what most machine learning systems are trying to do, it can also be seen as a form of coherence. Like you have one process running inside a machine, you have one process running outside of the machine. You want those two to be coherent, it means to come to the same conclusion. So it's one part of what I call this coherence, and there is even something called coherence epistemology, proposed by the cognitive scientist Paul Tegaard, where he shows that actually in the history of science, when one theory was replaced by another theory, it was because this one theory was more coherent with different kind of observations and theoretical assumptions. So this coherence criterion can also be applied to this prediction model, which is what most machine learning is doing.
So what's interesting is that we're living in a time of deep amnesia of our science, right? So the whole idea of value-based learning or utility-based learning goes back to Thorndike, late 19th century, right, with the law of effect. And now we have armies of engineers who are making a living exploiting this law of effect. putting likes on pictures and God knows what, right? Destroying, if you want, our society in the meantime. But the point was that people then try to pursue the impact of this kind of reinforcement-based learning very systematically, right? Because it was the idea that the agent is like this billiard ball driven by Newtonian forces, and the law of effect is one of them. Skinner made this an art, if you want, right? But Skinner then in the Second World War tried to sell his art as a way to control guided missiles with pigeons, because he thought I could train them with these reinforcement-based schedules, and they can guide any missile to any object I train my pigeons on. This was not a big success, okay? And that anticipated already then also the collapse of this whole behaviorist dream that we can control any agent with external forces like the law of effect. An example is, for instance, Rescorla-Wagner laws, 1972, that say learning is based on intrinsic properties of the agent. It is all tied and modulated by the predictions agents make, and this prediction will depend on the learning history of the agent. So at least since then we know that the law of effect is not a sufficient way to think about learning as it happens in nature, okay? But now it's still elevated to the level of a religion, right? Because reinforcement learning is everything, and we give the Turing Prize now to people who exploit this in different computational systems. It's just not the way brains work, because brains place at the center the acting agent with its own unique individual learning history. We know it. But if we want to now elevate technology to that same level of competence, this is the first thing we have to take more serious. Right? Learning agents learn as individual agents with the self. And if you look at the brain, of course, these simple observations about reinforcement learning were elevated to the level of fact, right? With this whole idea that dopamine systems would reflect these kind of reinforcement signals by Schultz and Diane and Montague and so on. But this was also a caricature of what brains really do, right? If you look at the data, the facts, an interpretation of novelty detection might be more appropriate than to say it's a clean reinforcement signal. Now, on top of that, if we delve deeper into how brains operate, the beauty of brains is they can adapt also their utility functions. That makes them so interesting. It's not about just pushing likes on a stupid picture, right? The brain can really dynamically adjust what its value function is. And this is how we develop different social cultural systems, where we have different normativities. Brains are able to incorporate these normativities and in that sense also reprogram their value functions. And that makes them so powerful, but also so dangerous. And that's why we have about 1,000 people in Silicon Valley destroying our society.
Yes, just to make a quick comment on that, there's a sense of irony in what you're saying also, that this is happening in Silicon Valley, where 40, 50 years ago, no, 50, 60 years ago already here in Berkeley, we had discussions about existentialism versus structuralism, which was exactly a similar debate about whether our purpose comes from the outside or whether it's intrinsic. And so,
that's what I'm saying. We're living in a state of deep amnesia.
Yeah.
And that's why we want to click the like buttons all the time. We don't need history.
So just to try and respond to the question of I think you asked, can machines learn by having sort of intrinsic
And what would it be like?
And what would it be like?
Yeah.
Right, and I don't have the answer to that. I personally think that my definition of machine is fairly broad, so I believe that we are machines, so I believe it could happen. We could build machines to do it. But it's a good question, what's needed? And clearly, I think one thing that's needed is the ability to predict the future, to have a model, a causal model that allows you to predict that if this happens, then something else is likely to happen, to be able to have an ability to generate counterfactual reasoning, to say, suppose that this other thing happened, this is what could happen then, and also to have a model of the self, an awareness of the self. If you don't have some kind of self model, I don't think that kind of learning can really happen, and today's AI systems really aren't focusing so much on that idea of the self model.
In fact, what would it be like? What do you mean by a self model? Just simply recursion model that basically you look at your output or you look, I'm not sure what the self would mean in this context.
Well, I mean,
Yeah.
I think in a way, your whole research career has been about what does it mean, right? But and nobody really knows because we don't know what we mean by the self, but somehow we have a way of reflecting on our own reasoning, our own thinking, our own. It's some kind of it's not just recurrent neural network that's getting input back, but it's which is not it doesn't have a model of that. There's something lacking there.
So I think we can be a bit more bold about self, right? There's certain things I think we can agree to very easily, which is all the selves we know are embodied to start with, right? So if you talk about what would it be like such a technology with a self, it by necessity is an embodied technology, right? It means it's in the world, physically realized, it has sensors, we can detect states of the world, and it's also then intrinsic needs that are supporting its survivability in that world.
But are you saying that you're saying every self in the world is embodied?
Yes.
Is that by definition, or is there some...
It's every self we know. How many selves do you know that are not embodied?
I don't exactly know what a self is, so I can't really say.
No, a self is, let's say, an agent with a unique identity, right, that is setting its goals for its own behavior, that is satisfying these goals that it is setting, right? We can just make a list of properties that will go in this direction. Would you object to any of these elements of a definition of self?
Would the term agent help you in any sense?
Well, that's the one I just used, right?
I think that it's possible if you gave me a list of such things that you might be, I mean, I haven't seen your list, but maybe it could be argued that actually there are programs that have these properties.
No, they're not there because, okay, but the point is, okay, you don't know what self is, that's fine, right? I don't have to convince you of knowing what self is because you already admitted you don't know. That's fine, okay, I respect that. However, I have a hypothesis what self is. And I keep it simple, I'm just saying, look, all the selves we know are embodied, so this is where it starts. And then from there, it has to bootstrap itself also in representing these self states and how they link to its goals, etc. So it's a bootstrapped, in the end, also representational structure. And with that, I think you have a pretty decent working hypothesis, which I don't think is unreasonable, at least as a way to start to test ideas about self. So if Terry's question is, what would, in your opinion, my opinion, a technology look like with the self? It's okay, it's embodied and it has memory structures to also develop representations of that self state and link it to its goals.
Bruno, have anything to say?
Maybe I'll just add that there's some real interesting work from one of my colleagues here at UC Berkeley, Fritz Sommer, where he's developed this model of learning they refer to as predictive information game, which is sort of similar to what people have been talking about prediction here. But it's where an agent gets rewarded for expanding information about its world, okay, for adding to its model of the world. And so it's kind of an interesting trade-off where where you're constantly testing your model and you get rewarded when your model is correct. And so there you would just sort of sit in the corner and stare at the wall because you'd always be correct. Versus exploring the world and trying to add to your model, right? So you have these sort of two terms which are always kind of there, and you get very interesting behaviors out of this. And something like that sort of seems more along a more natural way of sort of formulating the problem rather than sort of saying, you're getting these rewards from the environment, it's giving you sugar or juice and things like that. And it just seems a very impoverished kind of way of sort of dumbing down animal intelligence. But the other thing I would add to objective functions in machine learning is that, they're very simplistic, and animal behavior is extremely rich by comparison. And I have yet to see any kind of objective functions being used in machine learning which can really capture that.
Yeah.
So not very long ago, my computer crashed, and I got very angry at my computer. My computer didn't get angry at me for making it crash. And that's because my computer doesn't care about it crashing. It doesn't have anything to lose. I have my information to lose. So I would add to this potential list of embodiment and memory also the aspect of having something to lose for itself. And that maybe also makes it necessarily embodied, because I couldn't imagine how it would look like if you're not embodied, that you'd have something to lose.
Well, actually, that ties in with what I wanted to add. That is the idea that the self is something that is self-maintaining or self-producing, what some have called autopoietic. I wouldn't go that strictly to stay in the strict definition of Maturana and Varela of autopoiesis, because they are kind of religious about it. But I think that any self or any agent is something that tries to maintain itself. That means it doesn't want to die, it doesn't want to lose what it has, it wants to keep and rebuild the things it has. And any interaction with the outside world can either enrich it by giving it more resources to maintain itself, or can potentially destroy it. So learning a priori is trying to get to see how this environment functions so that you can extract the benefit from it, the things that allow you to grow and to maintain yourself, and how you can avoid the things that may destroy the things you have. So I think that's the essence of agency or of self.
So I like the way it's going. This is where I would, of course, take it. And basically, computers have no, as they say, skin in the game. Even a bacterium does. And I think one of the challenges we have coming out of the age of Descartes, as we are still in, that we think of self mostly from our cognitive point of view, subjective point of view, but self is what biology is all about. Biology is about maintaining self, reproducing self, repairing self, and our cognitive systems are, in a sense, playing that same role. And that's where they came about. So I'm not going to push this any further. I want to ask one more question before I open it up. And that is, there seems to be an interest in our community in general, and I think this is just about the curiosity of science, to want to build computers that have these kinds of functions, want to be able to construct devices that feel, that think, that have curiosity. First of all, whether you think we can do it or not is another question. The first question is it inevitable that we're going to go in that direction? And if we do, what are the consequences? Should we be going that direction? So it's both a moral question and a question about, is that where we're going?
So the reason I got into the field of AI was to try and understand this phenomenon called intelligence, and it seemed that this was one valid approach, was to try and create it, not just to understand a particular organism's intelligence, but to understand it as a more general phenomenon. So I think that scientific question has motivated a lot of people in the first place. Unfortunately, I think a lot of the sort of intellectual excitement of that kind has been displaced in the field by more commercial applications of AI, which is sort of sad for me. Good for my students who go off and work at big companies and get paid a lot. But I think that it like any technology, that it comes with a lot of dangers, you know, and you know, I think an analogous example is synthetic biology, which is also motivated by trying to both understand biology by creating living systems and also as a commercial or, you know, applied endeavor. And it comes with a lot of the same ethical issues as well. And I think that analogy has to be kind of fleshed out in AI now that we're sort of behind sort of the bioethics community in thinking through the ethics of these things. But I don't know if I think it is, yes, inevitable that this is the direction that science will take, because people are particularly interested in their own intelligence and trying to recreate it. But I do think that it is very dangerous, and we really should be worried about a lot of the things that are happening. So.
So Giambattista Vico was a 17th century philosopher in Napoli, and he deeply disagreed with Descartes and his model of knowledge. He said, no, dualism is not a way to understand these complex processes. And then he formulated an alternative approach, which the core consideration is that factum et verum convertitur, or it means the fact and the truth are reversible, right? So Vico said, no, we can understand the things we built. So this is where it all starts. And then he went off to study culture from then on, because he said that's the only non-trivial thing that humans ever built. And with that, he laid the philosophical foundations of the modern study of history. This is very much the paradigm we follow in our work. This is what we do, we call living machines. And also, we've just published a handbook of living machines. And the basic thing is, if you look at brains and minds, in my opinion, if we ever want to explain them, we can only do that by reconstructing them. Why is that? Well, I can give you a practical argument, right? Since the 80s, neuroscience has been importing armies of physicists, right? Who would tell us how the brain would work, because they discovered Hopfield networks that Ising spin models are really very simple. Now we're 30 years later. Do we understand how the brain works? Well, no, okay? But in the meantime, we had to digest a lot of equations. So what this illustrates is that there's a fundamental collision between these worldviews, right? So physics is great in closed systems where you can make assumptions about infinite time, infinite space, and so on. Biological systems just don't work like this, right? They're open, they're multi-scale, they're highly heterogeneous. We have no comprehensive frameworks to study these, certainly not from an analytical perspective. We just don't. And of course we can say, oh, we should do that. Yes, great, go off and do it. But it hasn't happened so far. And what I'm saying is the alternative is indeed to construct living machines. We have to build machines that incorporate the fundamental properties of biological systems. So that means it's not metaphorical neuroscience, it's real neuroscience. Physiology, anatomy, biomechanics, those are the constraints we really have to get our heads around and incorporate in these artifacts we construct, because these artifacts are going to be the models of these biological systems. It's the only way forward, because these are open systems. They learn, they adapt, and so on. But of course, that means in parallel, we will construct artifacts that are having the advanced capabilities biological systems have. So that is, if you want, the upside, but also in Melanie's perspective, and I agree with her, there is a risk involved in that, right? Because now we're going to build machines that indeed can adapt very rapidly to complex situations and maybe not follow ethical rules that we might want them to follow. Okay, but the bottom line here is that the machines we're going to see in the future will be more and more like the living machines we know, because it's the only way to actually really test our theories about them. Okay? And in addition to that, of course, humans have this vanity that we want to construct artifacts in our own image. And that's what plenty of people are doing, and they're building cute avatars, and they make cute little movies that look like humans or that look like the Mona Lisa, even though if you look at the details, they don't. It's a form of vanity. It's vanity science, vanity technology, and it's largely meaningless. Okay? The only reason to build these machines is to understand living systems.
I wanted to respond to Melanie and the idea that we should be afraid that it may be dangerous to build autonomous machines. I think we are too quickly frightened. I mean, we are surrounded by a natural world that is full of autonomous, unpredictable machines, namely organisms, people, societies, groups. All these things have these characteristics of being autonomous. I don't see why an autonomous machine should be necessarily more dangerous. Machines can be dangerous when they are very predictable and unautonomous. I think about an atom bomb or a machine gun. That is not what makes a thing dangerous. The fact that it is autonomous. Of course, if you make an autonomous machine, you maybe do not want to put it into control of some critical system like, let's say, a hospital. Maybe you want to keep it for things that are a bit less critical, but I don't see any reason why something that is adaptive, that is self-organized, that is self-maintaining, should necessarily be dangerous. It will just want, like us, to survive and to be good friends with its neighbors and not get into conflict and not kill people just for the sake of being a smart robot. I mean, all these kind of crazy scenarios about take over by the robots, I always tend to think that if something becomes incredibly smart, like an AI or a robot, it will somehow want to control everything and kill everything. I don't see any reason why it should. It's not in competition with us. It doesn't have any advantage in doing bad things to us. It just wants to survive.
Well, let me give you some reasons. Okay. I think your position is a little bit naively optimistic, because why do biological autonomous systems not self-destruct on a large scale, even though we actually are with a long time constant? We come pre-equipped with a number of priors that make us less dangerous. Like primates have priors such as reciprocity, right? As empathy, right? Look at Frans de Waal's work, for instance. It's by virtue of having these priors that multi-agent collectives can remain relatively stable. But if I now build a machine with a controller that's a psychopath, and I put this in a car, it can cause severe damage, right? So it's not the case we should just say like, well, autonomy itself is going to be dangerous. No, but it's all about the priors that we give to these systems. You know, I was talking to people at US Army Research who are in charge of this program for their autonomous tanks and trucks and whatever, you know? And they see this as engineering problems. So when you ask them about, but have you thought about some sort of control systems for ethical decision making, their eyes just glaze over, but they don't realize that without such a system, these devices will just drive over their own troops to get from A to B because they want to follow the shortest path, right? So to just say, look, autonomy as such is not threatening, I think it is, because it only is stable given the priors that are embedded in these systems. And if we don't understand that, we're going to cause a lot of havoc, which we actually do right now, right? There was, again, another article this morning about how the YouTube algorithms for search create actually advertising systems for child pornography, right? So these are real problems because we haven't understood how to regulate this autonomy, and biology has understood it.
Yeah, I agree with Paul here, but I would also, I just wanted to give a quote from Pedro Domingos, an AI researcher at the University of Washington, who said that he's not afraid that AI will become too smart and take over the world. Right. He's afraid that it's too stupid and it's already taken over the world. And I think that's more of my fear, is not that we'll have these smart autonomous systems that are trying to kill us, but more that we have these stupid sort of systems that we're allowing to be autonomous that we allow to destroy our lives.
Such as the ones that push the nose of the airplane down.
So I like the contents of this discussion. I mean, it brings to mind a thought experiment where we write fictional history, and we say, what if 100 years ago we had morphological computation, and we're now on the verge of inventing this sort of logical computation. What kind of arguments would we come up with? What kind of arguments to not pursue this would we invent? And I think we just heard a couple, which unfortunately are reality. But I think it would be interesting to contrast those arguments against the arguments against the systems we are talking about right now.
Let me just end by turning this around. We're all worried about what it's going to mean for us. To build a device that has its own normativity probably is a device that can suffer. And one of the reasons I began this conference with HAL being turned off in 2001, I can feel it. It's going away. I'm losing my mind. I'm afraid. We don't have any trouble doing this kind of thing to other creatures that can suffer, but we're probably crossing over the line as we build machines that are trying to keep themselves going, or having a worldwide intelligent network that is trying to maintain itself. Now we have a different ethical story. Do we have to worry about the ethics on that side of things?
You mean whether our autonomous systems could suffer and therefore we should not? Well, I'm not inclined to think that suffering per se is such a grave thing. I mean, suffering is part of nature. After all, I mean, whenever an animal is eaten by another animal, it suffers. As long as that is not, I would say, artificially prolonged, it's part of what nature is. You suffer as a kind of a negative feedback signal, like this is an experience that you should avoid. So suffering is part of being autonomous. It's only when you torture somebody that means that you artificially prolong the suffering that I would say that ethics is involved. But that occasionally things happen, that somebody suffers, yeah, okay, I think it's part of nature.
Well, we seem to disagree a lot, but it's not that easy, right? If you look at Bentham's utilitarianism and consequentialism in ethics, it's all about minimizing suffering. So you can really make a calculus, if you want, of suffering, and that should inform ethical decision making. And now with machines, we also see the limitations of utilitarianism, because you could say, well, if I have one machine that suffers because its user is torturing it or something, you can deploy 10 machines that are fully happy continuously, and then you should compensate, again, overall world suffering, right? So this is how you always can then escape, and it shows you the limitation of these ethical frameworks. So I think if machines will be afraid to die, which by necessity they have to be, as you also mentioned earlier, because that's at the heart of also being embodied and autonomous, then we do have to think about the ethical implications of that. And unfortunately, the ethical frameworks we have are just insufficient. And what's interesting about that is that ethics has evolved more driven by, let's say, the legal, economical challenges of our society. And it has sort of developed frameworks to answer those. And it has much less dealt with these very much existential aspects of what it is to be alive. And these are now the questions we have to answer. And unfortunately, when you talk with the ethicists, it's often like, well, let's do the precautionary principle. Let's just not make too much, let's not change the situation too much and see what happens. And then we can inform ourselves, right, how we can respond. And that's, I think, now one of our problems. So that's, as somebody mentioned earlier, we have to educate the engineers in ethics, and I think this is really becoming an issue. So I see that we have no answers right now. We see how existing frameworks are not necessarily answering sufficiently these challenges, and I do feel the researchers have to become part of this discussion much more than we have been. But yes, this is going to be a real problem.
All right, some questions. Just let's have someone come up and carry this microphone out.
Oh, thank you. Thank you. I have heard the word ethics said many, many times, and the second question that Terry asked was about values. These are complicated things, but I think the solution is very simple. And I'm encouraging everybody to have a look at this book. The first chapter is on science. The title of the book is The Meaning of It All by this guy, Richard Feynman. And the chapter 1 is on science. And the chapter 2 of this book is on values and ethics. And Feynman gives the answer, which is that science can't touch. That's not the role of science, that's the role of religion. And I highly recommend, I already see shaking of heads, I strongly recommend reading Feynman's book titled The Meaning of It All, and it is shocking. He uses religion. Now he's talking about good religion, but yeah, it's not.
That is such a bad example. I mean, Feynman wasn't in a happy project, right? And
Feynman talks about the atom bomb. He talks about it. You know this book?
Sure, but
good.
But the point I'm making is exactly the answer is to say, no, science has to become part of this debate. We left it, we have decoupled ourselves from the debate, and now we face these challenges we cannot answer, also ethicists cannot answer. So I'm exactly arguing against Feynman, who has been wrong also on other occasions. I mean, he might be a smart physicist, it doesn't make him a smart on everything person, right? So this was a valid point at that point in time when people believed also the two cultures, for instance, of J.P. Snow. Humanities and physics will never meet, they're different worlds. Well, okay, that was the 50s. The world has changed a lot. We're facing problems of which these traditions are at the source, and now we got to solve them by questioning these traditions, okay?
So, yeah.
All right. So, I mean, a very common example that's used in machine learning and also in teaching is that of the two rails. One with one person lying on it, another with 5 persons on it, and you have to can you pull the lever? What do you do? And I think this has been misinterpreted very often because engineers approach this as a mathematical formula. They try to provide a scientific answer to that, and they say, well, it's easy. You just switch the lever and only one person dies. And the example is actually quite the opposite of how it's meant to be. I think the answer to that question is there is no answer. It's what we want or what you want. It's the ethics of this example is not something you can simply calculate or prove. So in that sense, I do agree with maybe not the answer to be found in religion itself, but whether this is inside the scientific domain, that's it's something I would agree with, that question.
I want to say that actually I agree with Paul. He thinks we always disagree, but
It took some time.
I do believe that ethics and science should not be separated, and I think that the classical idea like Feynman that values are something that we should leave to religion is really stupid, because where does religion get it from? Some books that were written millennia ago, which do not apply to our present society. We have to think for ourselves, and that's what I wanted to say about the complexity of value systems. The objective functions or the utility functions used in machine learning, we all know they are much too simple. There is no simple objective function that we can define. So if we think of it purely in the traditional reductionist scientific way, we will not solve the problem. That's why we need to have a concept of values that takes into account this whole complexity of a network of agents interacting, and where these agents can either get into conflict and friction, or they can go into what I call coherence or synergy. That is this kind of more global encompassing view of values, but that means that you understand interaction between lots of agents, and that is a scientific problem which we're starting to get a grip of thanks to sciences of complexity, self-organization, nonlinear systems, all these different algorithms. Evolution of cooperation is quite a lot of research that has been done on that, and that is informing us.
I agree. Let me send this out.
I'm going to head back here first.
Thank you. This is a good transition for the question I wanted to ask. Religion is not just one thing. It is right now especially more associated with absolutism, extremism, fanaticism, essentially ever-sharpening divisions of one kind or another. But the religions I admire also preach and often deliver peace, equanimity, understanding, empathy, a lot of much smoother, blurrier, more generalizing things than sharpness. So that's sort of a thermodynamic spectrum of the kinds of religion you might have or not have. But that brings it back to the physics. Imagine a single counterfactual. Imagine if no one had discovered neurons 150 or so years ago. Interesting little cells. They were powerful enough to deflect the metal needle on a galvanometer, which is quite a bit of energy for one cell. But imagine we'd never discovered there were cells which made clicks and pops. And we had continued seeing the world as a three-dimensional continuous place and imagining our brains as some sort of fluid which reflected and matched the world, like the shadows on Plato's caves. If we hadn't discovered neurons, we wouldn't have had the McCulloch-Pitts version of the neuron, we wouldn't have had the binary transistor, we wouldn't have had vacuum valves and then transistors and so forth. We wouldn't have digital technology or programming, and we wouldn't have neural nets. So if you yank out computation, yank out both digital computers and neural nets from it, what would we have?
Yeah. Do we have answers?
Counterfactuals are difficult things, right? And So I think it's not helpful the way you phrase the question, because we also can think about the progress in concepts and ideas as transitioning, right? As building one layer on top of the next. And in that sense, if at this point in time, right, like 70 years post-Turing, when he proposed his solution to the Entscheidungsproblem, if we now say, well, now it's not computation not sufficient. It got us a long way, but it's not sufficient. Then to jump back to say, hey, but wait, you cannot reject it because I could not imagine a world as it is now without that concept. I don't think that's really the way to think about it. It got us a long way, but it also might have gotten us now into a bind, and we have to rethink what our next step is, right? So I don't see it necessarily as a fatal loss if we decide let's move on beyond computation, right? So in that sense, I sort of don't accept the counterfactual as a useful lever to think about this next step intellectually.
Can I recommend that, Todd, I had hoped that you would be here earlier, but I would love to have your last word.
I guess the way I think about these difficult problems of ethics and technology is that the technology is part of the society in some way. And so just as the society shapes the ethics and morality that we've had for a long time, those forces will come upon our technologies as well, maybe in a somewhat different way, but I imagine these very complicated problems like, do I run over the grandmother or the small children, will ultimately be decided in a court somewhere. And the way it will be decided is that it costs you this much if you hit the grandmother and this much if you hit the children. Okay? I mean, this is actually the way it functions today, right? So somebody's going to make a court decision that says, autonomous cars, every time you hit somebody, it costs you this much money. And somebody's going to do a calculation and say, okay, well, I can live with that if it's my autonomous car business, if I can do that. And I think that's actually how those decisions will be made. And so the technologies will press upon us by changing the world, and we will press upon the technologies and the people who use them to do certain things.
So Todd, I'll just press you one last time on this question.
Yeah.
And that is, are we faced with new kinds of moral questions because of the work we're doing? I could have asked you this same question if you were a synthetic biologist. Are there new kinds of ethical questions, new kinds of ethical problems that we're now about to face?
Yeah, I think there are. I mean, it's sort of like, before we had nuclear weapons, we couldn't kill whole cities at a time, right? And so when we had them, we suddenly had a whole bunch of new issues, and there's a whole history of what people had to do to deal with those things. I think part of the challenge with our technologies is scale, right? It's not like, it's happening just in my house, so to speak. These global networks we have affect enormous numbers of people in ways that they haven't yet. And so I think it is different. I just think that the solution will be somehow the same old, same old. We will still have court cases and arguments, and we'll come to some messy compromise, and a lot of that will get baked into our technology.
So I want to thank you all. It's now time that we should all race to lunch, but thank the panel, and